Today's goal is to factor quadratic expressions. In order to know what that means, we need to first talk about some vocabulary. We use the word factor in two different ways. We can use it as a noun, in which case a factor is a divisor. For example, 2 is a factor of 6, since 6 divided by 2 is 3. There's no remainder. But 2 is not a factor of 7, since 7 divided by 2 is 3 with a remainder. 2 does not evenly divide 7, therefore 2 is not a factor of 7. But we also use the word factor as a verb. To factor means to divide. For example, we could factor 6 into 2 times 3, and we could factor 7, well, only into 1 times 7. An expression is a mathematical object or a mathematical thought. It does not have an equal sign. So, for example, 3x minus 4 is an expression. 2 root x minus 5 over 4x cubed is kind of a weird expression. But if we said 3x minus 4 is equal to y, now it's a function. If we said 3x minus 4 is equal to anything else with just x's in it, now this is an equation. So an expression is a mathematical thought with no equal sign. Okay, so, this last word we need to talk about is, what does it mean to be quadratic? We're factoring quadratic expressions. That means we're dividing mathematical thoughts, not equations, not functions, that are quadratic. Quadratic is an adjective. It's an expression that can be written in the form ax squared plus bx plus c. This is called the standard form, the typical form of a quadratic expression. You'll notice that it's got an x squared term in it, and then it doesn't have other stuff like square roots and fractions and things like that. So for example, 2x squared minus 4x plus 1, that's a quadratic expression. 2x squared minus 4x plus 1 is y, that's a quadratic function. And in fact, 3x squared minus 5 is also a quadratic expression because that's the same thing as 3x squared plus 0x minus 5. It can be written in this standard form. Things that are not quadratic, a couple examples would be like 3x minus 4. There's no x squared term, so this is just a linear expression. If we add in like things like square roots or we put x's in the denominator of a fraction, these are no longer quadratic. Okay, so what does today's aim mean? We're factoring quadratic expressions. That means we're dividing mathematical objects that take this form, ax squared plus bx plus c. Okay, let's get to it. There are two different strategies we're going to use today. The first strategy we're going to use is to look at the two terms and ask ourselves, do they have something in common that they can be divided by? For example, x squared minus 36x, you can divide both terms by x, so we're actually just going to divide out that one term, and we're done. This is the factored expression. If you want to double check, you can distribute the x. And indeed, we got what we started with. So we factored it, we just divided it. Now let's take a look at the next one, 15x minus 20. I notice I can divide both of these by 5. So I'm going to divide 15x by 5. I'm left with 3x. I'm going to divide 20 by 5. I'm left with 4. And again, if you would like, you can distribute to double check. Now, negative x plus 7, they actually don't have anything in common, but I do like that first number inside the parentheses to be positive, so I will just divide both terms by negative 1, and I'm left with negative 1 times the quantity x minus 7. Okay, let's take a look at another one. In example 2, I can't start by dividing all the terms by something. I could divide these two terms by x, but I can't divide 15 by x without some nasty remainder. So instead, I need a different strategy. I'm going to call this the two-number strategy. I'm looking to find two numbers that multiply to whatever this c term is, right? We'll put this in standard form. It looks like ax squared plus bx plus c. So my c term is 15. I need two numbers that multiply to 15 and add to the b term. In this case, the b would be negative 8. And I'm thinking, what numbers multiply to 15? Well, 1 and 15, but they don't add up to 8. That won't work. 3 and 5, well, they'll add up to negative 8 if they're both negative. So I can use negative 3 and negative 5. So I'm just going to write out the factors, x minus 3 times x minus 5. It should work, but we can multiply to double check. I've got x times x minus 5, minus 3 times x minus 5. And indeed, they multiply to our original expression. So by factoring it, we mean we divided this expression into this term. Okay, let's take a look at our next and final example. We're going to express two different expressions in factored form. To express in factored form, that's the same thing as saying we're just going to factor or divide these two expressions. Okay, take a look at this expression here. It's in standard form. It's a quadratic expression because it's got that x squared. And I see that we can't divide all the terms by something. We could divide these two terms by x, but we can't divide 32 by x. So instead we need two numbers that multiply to that c term to negative 32 and add up to the b term, so they need to add up to negative 4. Okay, let's try some numbers. 2 and 16, those won't add up to negative 4. What else can you multiply? Oh, 8 and 4, well, they will multiply to negative, or I'm sorry, they'll add up to negative 4 if the 8 is negative. So I think we can factor this expression into the quantity, x minus 8 times the quantity, x plus 4. I believe that's our factored or divided term. Final answer, but let's just double check. You can check using your favorite multiplication strategy, whether it's double distribution like we did here, or you like using the box method. And indeed, we've got x squared. When we combine these two terms, we have minus 4x minus 32. That worked. Good. Okay, we've just got one more expression to take a look at, x squared minus 36. Now you may be saying, first I'm going to try to use greatest common factor. That's our strategy from example 1, the greatest common factor, the divisor that these terms have in common, or both have. Well, that's not going to work because you can't divide x squared and 36 by any of the same thing. Now, there are actually two different ways that people think about this. Some people are going to say, well, this looks like x squared plus 0x minus 36. There's not an x term, therefore the x term is 0. Now, this is a quadratic expression in standard form. Well, that's nice. Then I know what to do. I need two numbers that multiply to negative 36 and add up to 0. Well, if they add up to 0, I'm looking for numbers like 4 and negative 4, 5 and negative 5. Oh, 6 and negative 6. That will work nicely. And you can double check. When you double check, these terms do indeed cancel out. So you're left with just x squared minus 36. So that works nicely. If this strategy seemed confusing to you, you can also think of this as a difference of perfect squares. I'm saying difference because I see two terms that are being subtracted. And this is like a really special case because x squared is a perfect square, it's just x times x, and 36 is a perfect square, it's 6 squared. And so indeed, if you had like x squared minus 9, you can factor it into x plus 3 times x minus 3. You need the positive and the negative term to add up to this 0, or even 4x squared minus 100. You can check me on this. Oh, that'll simplify. 4x squared minus 81 would factor into 2x plus 9 times 2x minus 9, because when you double check, you'd get this 18x and a negative 18x, which will add up to 0, which is that missing term there. So you can think about this in two different strategies. The two numbers strategy, two numbers that multiply to c and add up to b. You can think about the other strategy as GCF. If it helps you, you can think about this as being a third strategy, the difference of perfect squares. Or you can simply think of difference of perfect squares is one example of our two numbers strategy.